All right, good afternoon, everybody. So what I would like you to do is go into your midterm folder that you created in lecture 14. There's also the directions on how to get the code that we're going to do today. We're going to finish off problem 5, and then I'm going to show you how to make sure you get your full credit for the exam stuff. The other thing I want to mention really quick while you are all doing that is I'm going to bring up on the back end of Sakai just to kind of show some urgency here. So the pre-internship bidding, for those of you who had lab yesterday, many of you have already done it, but also notice how it says 20 are in progress. Please make sure that if you have already put in your information and submitted it, make absolutely certain. So make sure you get it in on time and that your choices are in there, so that way when I run the algorithm tomorrow morning to set up the teams, that your choices are in there. If you have lab today and you don't know what I'm talking about, I will explain everything in detail in lab. So what I'm going to do is I'm going to go over initially to the right board here, and I'm going to show you, if you look at the bottom in main in problem5.cpp in the source folder, I am at your right, my left, my apologies. If you look at the source problem5.cpp in main, you're going to see that I have a vector of standard pair of integers. And in that standard pair of integers, it looks as follows. It'll be 0, 1, 0, 2. So I'm going to write this up at the top. 0, 1, 0, 2, 1, 2, 1, 3, 2, 4, and 3, 5. So an ulterior motive with this kind of problem. We're setting up to use the data structures that we have built so far this semester to build a new data structure called a graph. Those of you who've taken discrete mathematics, you're probably very familiar with some graph theory. You're probably familiar with depth first search and breadth first search. You're probably familiar with Dijkstra's algorithm. If not, that's okay. We're actually going to be going over all of those again with the added emphasis of we're going to implement it in code. So what these are actually origin and destinations. We're actually going to revisit the idea of nodes that we used when we first started doing linked lists. So this is actually a graph, and I'm going to start putting in nodes here. This will be node 0. I'll say node 1, node 2, node 3, node 4, and node 5. And so what these are, this is actually 0 to 1, 0 to 2, 1 to 2, I'll draw that correctly, 1 to 2, 1 to 3, 2 to 4, and 3 to 5. And so what happens is it passes it to the function, and it creates an unordered map, so it creates a hash table and a stack. And the unordered map is an int and int, and then the stack contains pairs. And so what we're going to do is we're actually going to write a rudimentary algorithm known as depth first search. And what we're going to do is we're going to go through and we're going to check to see if the pair that we're looking for is already available. So we're going to iterate through the pairs. And what's going to happen is we're going to start here at 0, 1. And it's going to say, well, if we haven't encountered second. So what's happening is the first 2 lines we're going to write, we're going to insert the beginning with 0, the dot first, and -1. So the pair is actually going to look like this, 0 and -1. The reason why that's going to be is because we're going to use that -1 as something called a sentinel, where when we're going to go back through the stack, when we get to what we're going to call the origin of the graph, or the origin of our search, when we reach that -1, that means there's no other parent, and therefore, when we can go backwards, we can use this to take advantage of determining the full path. And so the second one, which we're going to write the code here, begins a vector that begins second, so it's going to be 1 and then 0. So what we have here is the parent for the beginning is -1, 1's parent is 0. So it looks like this. And then what we're going to do is we're going to iterate through, and if we haven't encountered this particular value, we're going to put it into the hash map. So we get to 0 and 2, and we look at it, we're going to say, well, have we encountered 2 yet? that's going to be dot second. We haven't, so 2's parent, in this case, is also going to be 0. Then we're going to go through and say, well, 1, 2, have we encountered 1 yet? No. We're going to say that 1's parent, so we have, so we're not going to put it in there. I'm sorry, we have, I apologize, 2. We have encountered it already, so we're not going to hash 2, 1. Then we get to 3. Then we say, all right, 3, comma 1. We get to 4. We haven't hashed 4 yet, so we're going to say 4, 2. And then we get to 3. We haven't, we get to 5. We check second, so we haven't got that yet, so we have 5 and 3. And so what this means, and I'm going to switch colors here, is that we now have established the parents for a specific path. So what we have here is 1's parent is 0, 2's parent is 1, 3's parent is 1, 4's parent is 2, and 5's parent is 3. So that subgraph of those edges, that's the minimum number of edges that we need to be able to connect the entire graph. Does everybody see that? That is what we're going to cover on Thursday, and it's known as a topological sort. And so what happens is we're then going to see if we can figure out the path backwards from 5 to 0. Because our goal is to figure out if we can figure out a path from 0 to 5. So we have 5 to 3, and then we would actually put it on the stack. So we have 5, 3 here. Then we go to 3. What's 3's value? 3, 1. Then we look at 1's value, 1, 0. And then we look at 0's value, 0, negative 1. And now we've found where to stop. And so now what happens is 0, 1, 3, and 5. This is the resulting path that we can use to find the path from 0 to 5. So we're actually going to go over 2 different algorithms to accomplish this, but this is kind of a setup for what we're going to do. So we're going to start out by coding this, and then I'm going to ask you a question about something that's clearly wrong with what I have set up, and that's how we're going to apply our knowledge to data structures to be able to make a more advanced graph. So let's go back in to problem 5. And I want you to go to the line after. I want you to go to the line after where we do the specific input. So right here, this is what your problem5.cpp looks like. Your problem code starts here. And so what we're going to do is we're going to do that initial step. We're going to do 2 inserts. So the first we're going to say the map.insert. And this will allow us, again, if we use our brackets, we can instantiate a standard pair. And then graph vector is what we bring in here. So it's going to be graphvec.at_begin. And that means that we can do this starting at any location. And then we want the parent to be negative 1. So that's where we start out there. And then the second line, what you can do is you can copy it. And then you can have this as end. I'm sorry, not end, I apologize. This should be begin.second. And then this other one here will be begin.first. So this one should also say begin.first. And so let me write up what this is doing as you all are continuing to type in. What we have inserted is that we have 0 and negative 1 in the hash. And now here, second, that becomes just 1 and 0. So now we've initialized going through that process. Does everybody understand that so far? I'll give everybody a split second to continue typing. What we're going to do next is we're going to do that process of iterating through the pairs and checking to see if we have found it or not. What is the method that we use in the standard C++11 library that we determine whether or not it contains a key? Does anybody remember? Remember, we wrote this contains method, and I said it won't have contains until until standard 20. How do we? Yes. Count. Very good. That's absolutely right. We're going to go through and we're going to count the results here. So let me clear this up, and I'm going to Clear? I'm going to scroll down just a little bit so that way this code is still available for you. So we're going to initialize the traversal. And what's going to happen is we're going to use the new iterator that I taught you in the coding challenge 4, I believe. And we're going to say pair. And I'm able to say pair because I have a pound define directive for standard pair. And we're going to template it to int, comma, int. And I call it current pair. And that's going to come out of the vector graph vec. And in the comments, I should say check all the edges. It should be below here, but I'll just put it there for the time being. I'm going to say if we haven't used it using the count method, if the map count and here's the thing, which one should I use? Based on what I wrote up there, should I use dot first or dot second? Any guesses? Feel free to ask or engage on the Slack as well. Let me check, see if there's any chat. So what we have here is I'm iterating through the rest of this list. So what happened is I have 0, 1 as the first one, and I have 0, 2. So have I encountered 2 yet in that set of pairs? So I did 0, 1. Have I encountered 2 yet? So I want to determine whether or not I can get from, and how I want to get to the node with 2. So therefore, which one do you think I should use? Should I use the first one with 0, which we've already encountered, or 2, which we haven't encountered yet? All right, I see a lot of 2s. Very good. We want to do dot second here. And I see that's the same thing going on in the Slack. So outstanding job to everybody who responded there. So we're going to say current pair dot second. And we're going to say that this is the case if it equals 0. Then what we're going to do is we're going to say, we're going to insert it. So we're going to say the map dot insert. And we're actually going to put in second first. So we're flipping them. Cur pair dot second, comma, cur pair dot first. And so that's the whole thing inside of this particular for loop. And so once we've done that, now we have everything set up to be able to check. So now what we're going to do is we have, if you don't mind, I'm going to scroll up here just a moment. I'm going to show you that one of our inputs is int end. And so that's going to be our destination. And so what we're going to do is we're going to start at the destination and work backwards. And we're going to put those elements into the stack. And that'll allow us to be able to, because we're using last in, first out, the last element, which will be at the bottom of the stack, will be our destination. And the element at the top of the stack will be our source. And so what I'm going to do is, does everybody have the lines at lines 20 and 21? All right, so I'm going to scroll past that, and I'm going to get to the point where you can see it. For what I have it at line 37. We're going to start at int value is equal to the end. I'm going to say while value does not equal -1. That's our parent sentinel. And then I'm going to say value is equal to the map value. And so what that for loop is doing is it's saying, all right, I'm going to start at the destination. I'm going to keep going until I've found the source. And then after I do everything inside the for loop, I'm then going to update the value to the hashed result. So I put in that value as the key. That value is the previous, was the source of the edge. And so then what I can do is I can put it into the stack that I've created. I'm going to say the stack dot push. And then I'm going to do a standard pair here because let me scroll up a split second. You see that I've put the stack as a pair. So now what I'm going to do here is I'm going to put it as a pair, and I'm going to say cur pair first. I'm sorry, I'm going to say value, and then the map value. We use the brace here, and now we've pushed it all in there, and now the first values that we're going to have are going to be our destination. So that's going to be our final while loop, which we have here, has been provided for you already. All right, does anybody have any questions about that before I go into compiling and showing you how to get the result? Yes. Sure, I'm going to put it back up to the top for just a split second. Do you mind if, because I have it saved, do you mind if I go and compile and show everybody and then put it back up for you? So what I'm going to do is it's been updated here on FileZilla. There we go. So now I'm in a midterm folder. And if you have everything, you probably should see prob1 through prob4. I'm going to run make prob5. So if I've done everything correctly, it will compile. And then if you run it again, you'll see this prob5.txt and prob5.txt. We'll have 0, 1, 3, and 5, which is the correct path in that graph. So let me put this down and put the code back up here. If you don't mind, I'm going to zoom out just a little so that way you can see everything that we coded. And what I'm going to do is I'm going to venture back over to the right board where I drew everything up. And while you're finishing up, for those of you who are done and have it completed, I want to ask you a question. My question is, what do you think is wrong with the graph that I've presented here? Now, I want to say it's technically a correct graph in the most technical of senses. It is a graph, but it's kind of useless. How can I make this useful? And I'll give you a hint. Think of the name of the course. Any ideas? Yeah, you have your hand up in the back? No one? What could be a potential issue if I want to make this as a data structure? Does this graph have any data? Forgive me, I didn't bring my phone over, or else I'd be looking at the Slack. In fact, let me go back over there and I'll take a look. What is actually being represented here in that graph? I see. What's that? It's just a graph, and most importantly, the only thing that I have are destinations. Right? It's just structure. So if I wanted to make this valuable in anything, if I wanted to actually connect pieces of data, let's say I change this, I'm just going to change this to a character. I change this to A, B, C, D, E, and F. If I change that and I brought in the standard pairs, if I have A to B, A to C, and so on, is that any kind of useful? Why won't that work the way that I have it constructed? What's an issue there? Yes, go ahead. Give it a shot. No, there are no wrong answers. Yes. Oh, no, I'm talking about, like, let's just say I filled it out properly. Yes. Okay, so the crucial part is A represents some sort of ASCII value, right? I lucked out when I created an integer in that the integer location in the graph also contained the value. Does that make sense? So if I don't consider that, there's no actual way for me to be able to tell. If I have some sort of ASCII value, A and B, I can't actually figure out how to do the reverse there. So it's actually just structure. It's not a data structure, it's a structure. So what we're going to do when we write up our graph today is we're actually going to ensure that our graph has data and structure together. Right? And so I saw a quick question in the Slack about the for loop. The for loop, again, is just going through, and that's setting up our path from the beginning to the end. So by putting it in there, if the destination hasn't been found, we say that's going to be our path. Does anybody have any other questions? So if you run it and you have pair 5, and you have it all set up, is it actually going to let me out? There we go. And then you run test.sh, it'll say 100 out of 100. Once you have that and your TA verifies that you have that done, you will have that 100 points added to your midterm exam. If you run make clean, it won't delete any evidence that prob 1 through prob 5 were done. You see that they're still there. So once you do that, I want you to go up and then go into that new lecture 15 folder that you created. And if it works properly, just like I have written there, you're going to have several folders. And what we're going to be doing is we go through the graph design and construction over the next 3 lectures. It's going to be broken down into pieces. So that way you can see in small pieces how things were constructed, what was added to address another task. And so there'll be several different versions until we get to a final graph that's going to be able to contain everything we want it to contain. It'll be able to do breadth first search, topological sorting, depth first search, minimum spanning trees, Dijkstra's algorithm, and the A-star algorithm. So let me slide here. And so this is the purpose of the for loop, just to address that other question. We get here, it doesn't work out. And that's what ends up going into the stack. And then that is what is produced. That is the code that you wrote. And that's the remainder of the code in there. And there's, I've explained what's going on in the coding challenge. So now what I want to do, sorry, let me So now what we're going to discuss are our graphs. So a graph, we want to be able to come up with a way to be able to represent paths to different values. So we call them nodes, and we've discussed that the idea behind a node is that it contains data and then where to go to the next location. We've studied this so far in a singly linked list where it has a node and a pointer to the next node, and a doubly linked list where we have a pointer to the previous node and the next node. And the million-dollar question is, well, what if I want to have a node that can go to several different places? And I want to be able to account for that in my design. So you're on campus at Notre Dame, there's several roads that go outside of Notre Dame. And when you run your algorithm to figure out where you want to go off campus, you have to be able to figure out the correct road. You want to head north when you need to head south for a long time. You want to make sure you're going out the correct path. So just to quickly review, the origin was from the 7 bridges of Königsberg problem, where the question was posed by the mayor in the late 1700s. Is it possible to cross all 7 bridges without going across any bridge twice? And it was actually an important problem because it was a sailor's port, and people want to be able to get all around the town to be able to get supplies before they continued on in the fastest possible way. So it's actually a problem of great interest. And so Euler, he realized that where you started had nothing to do with the problem and defined all of the different locations as nodes. I know I've said this to you before, but I just want to review to refresh your memory. So what he realized is that Königsberg, instead of thinking of as just 7 bridges and trying to figure out how to start from any of the specific location, basically figured out that it's really 4 nodes. You have 2 riverbanks, and then you have 2 islands in the middle. And they're all connected by 7 different bridges. And so he called it a node, and he eventually called it a geometry of position, which eventually became known as graph theory. And then he defined a term called node degree. The node degree is the number of edges that are being used to correlate that a given node encounters. So with a singly linked list, the head node has 2. It has a head pointer that it's pointing to, and then a next. Every other node in the singly linked list has to itself because it has an incoming and outgoing. I'm sorry, this is head pointer 3. And so with the doubly linked list, you see that it's changed because you also have to account for the head and tail pointers. So going back to this exam problem, I was trying to ask you to come up with the issue with the graph. And the issue is, well, we want the vertex to be able to represent anything. Northern bank, a specific, trying to get to a specific path, specific where you might be at a specific dorm, or Fitzpatrick Hall or Steppen Center. How do you get to specific places? And you don't want to just use it as 0 or 1 because it doesn't contain any data. So you have to make sure that you can actually template any graph that you're using so you can use it for all these different advanced graph problems. So machine learning, graph theory is the foundation of what you would learn in a machine learning problem. So if you're planning on using something like TensorFlow and you want to be able to train a neural network, a graph is used to basically represent nodes in the neural network. So we need it to be able to represent whatever we want it to. So for the rest of my discussion of graphs, what I'm going to do is you'll hear me refer to a node as a vertex. So in a lot of graph theory, nodes in graphs are referred to as vertices. And I just want to point out, because it's a common question I get, that vertex and node in this context are synonyms. So now what I've done here is I have a different graph, but now my graph has data. So it's an integer and an integer, but what's going on is the location are still 0, 1, 2, 3, 4, and 5, but now the data inside of it is 4, 25, 10, 30, and 18. And this is important because if I used it the way that I did over on the other board, it would try to find the source is 4, the destination of one of the edges is 20. If we try to say that's location 20 instead of data 20, and there aren't 20 nodes in the graph, it's going to think that there's no path to 18, even though the path to 18 exists. Does that make sense? So this is kind of what I was trying to go to when I was over on the whiteboard about what's the issue. Is that you could potentially exceed the bounds of your graph. And so another thing, a common issue with graph design is going all the way back to void pointers, we learned about this concept when we discussed the difference between the location of a void pointer and the data of the void pointer and this idea of dereferencing. That was to give you a good foundation of how to understand good graph design. So if we need to design our own graph, here are some pieces of information we need. We need to know the location of the vertex, so we have to have some way of knowing how to find that on the data heap. And we need to know the data that's contained in the vertex. And we need to have some sort of representation of all of the outgoing edges. One important thing that will save you some time, some code, and some memory is that if you're at a specific vertex, all of the edges at that vertex have the same origin. So if it's already there, there's no need to replicate and store the origin of all the edges. You only need to store the destination of the edge because you're at that specific location. Likewise, with an edge, I need to know maybe the origin, I need to know the destination, and I need to know what we're going to say is the weight of the edge. We're not really going to go into it that much. We're going to go into Dijkstra's algorithm, but in the algorithms course, you're going to go into a lot of detail about how weights of graphs affect your traversal through a graph. You're going to learn about max flow, min cut. You're going to learn about an algorithm called Ford-Fulkerson. And the weight of a graph's edge becomes very important when you encounter that in your studies. But for right now, the big thing to note is that you have some sort of weights on the edge. And if we add some sort of weights correlating, if I have two paths between here and Indianapolis, and one has a lot of traffic and the other one doesn't have a lot of traffic, I can use weights to represent which path I'd rather take. Say, And then everything I just said is right there. So now we have enough information to formally define a graph. So first, we're going to say that a graph, you'll typically see it as G equals parentheses V comma E, where V is the set of vertices and E is the set of edges. So first, let's define V. V is the set of vertices, and what we need to do is we need to make sure that we account for that in some sort of ordering. Furthermore, we have an entire set of edges, which is E. And that notation is all of the edges that are going from one vertex in the graph to another. And by the way, for those with how many of you are now familiar and have learned about finite state machines? Is that something you've all, no one? Okay, so short version, you may have an edge on it that goes from a vertex back to itself. And when you cover finite state machines, that'll be something that will be very helpful for you. So now we're going to define a term called adjacency, and it's going to drive what we're going to do for the rest of the lecture. Adjacency is when I can say that I can get directly from one vertex to another vertex. Specifically, we will say two vertices are adjacent if there exists an edge between them. So here I have the edges between the nodes containing the data 4 and 20. They are adjacent because there's an edge. 4 and 18 are not adjacent. There's no direct path between those vertices. And being able to represent that is a crucial aspect of graph design. Does anybody have any questions before I continue? All right, so if we're defining the whole thing, the vertices are containing 4, 5, 20, 10, 30, and 18. And the set of edges, I'm using the locations here. And the notation is origin and destination. So we can tell the difference between the origin and the destination of those values. So now what I want to do is tell you about two different ways we can represent graphs in a computing system that are efficient. The first way is what is known as an adjacency list. So what I'm going to do is I'm going to create a dynamic array that has all of the data as well as the location. So here what I have is 4 and 20. 4 is located at 0 and 20 is contained at node 1. And I see that I have a representation of an edge at node 0. Next, I'm going to add another vertex containing the value 5 at location 2. And we see that I have this ordering here. And this ordering is going to become important in both breadth first search and depth first search. Do the same thing with 10 and 20 in the value 3. Then I want to add another vertex and another edge. I do the same thing here with 20 and 30. I put in 2. 2 to 3 contains an edge here now, so that represents from 5 to 10. And I can keep going. And what I would like to ask is, can anybody think of any drawbacks to this specific approach? Any ideas? Yes, in the back. All right, so you can't go backwards. We are going to get around that problem using recursion. So it's particularly with depth first search, we're actually going to use recursion to ditch that. That's a very good guess. Any other guesses as to some issues that we have? Yes. All right, so we got to start thinking about memory considerations. Another consideration that we need to bear in mind, I see that there's some typing going on. Another big thing is, can we determine quickly whether or not two vertices are adjacent? So let's say I want to determine whether or not 0 and 5 are adjacent. I can't just do this immediately. I'd have to go check through the entire list here. So therefore, the search time to get from a one location to the other from any two locations is known as big O of V plus E in the notation. But we can't go from 2 to 4, so that's a question, because I do not have an edge here. So it's just 0, 1, 2, because there does not exist any edge. Nikita, did that question address your question? So now we have another way, which is an adjacency matrix. An adjacency matrix may be used to represent in the graph by just saying whether or not there exists an edge between these values. So I go through the whole creation. We have the origin on the top and the destination on the left. And then I go through this process of creating the adjacency, filling in all the values in the adjacency matrix. Can anybody think of any drawbacks of this approach? Yes. Uses a lot of space. That's absolutely right. The big issue is if you have a lot of vertices but not a lot of edges, that is what's known as a sparse graph. And therefore, an adjacency matrix representation would take up a tremendous amount of space for not a huge graph. And so that's what we have here, space efficient when G is sparse. So, but what you said was correct. I mean, the memory can cause issues specifically with trying to get through each location in the adjacency list. And so again, here's the whole, I drew it out, big O of V plus E. Here, its space complexity is big O of V squared. You have to have something in the trap for every single origin and every single possible destination. So what I want you to do is we're now going to work on problem 1. So in problem 1, what we're going to do is we're going to go, I want you to go into that folder, lecture 15, and in the include folder, there's a file edge.h. And in that file, it'll look simply like this. It'll say lecture 15, problem 1 starts here. So what we're going to do is we're actually going to, using our knowledge of what we've learned so far in lecture today, design our own edge. So when we have an edge, what were the two things I said that we needed when we know that every destination, every edge has the same origin? So what are the two other things that we need for an edge? I'm sorry, what? Maybe I'm just hearing things. What were the two other things? So I have two vertices and I have an edge between them. I know where the origin is. What are the other two things? Yes. Destination, that's one of the two of them. Very good. What's the other one? Yes. Okay, so we don't need the source because we know we're at a specific vacation. So what's the other thing that we need? Yes, Simran. The weight. Very good. So that's what we're going to fill in. So we see origin, destination, and weight. So we're going to have, because this is a struct, we don't need public and private. So we're just going to say unsigned int destin. And then we're going to have an int weight. That's another thing that you'll go into in a lot more detail in algorithms. You can have negative edge weights. The next thing we're going to do is we are going to write 3 methods. The first 2 are going to be constructors. So I'm going to do an edge, and then do a member initialization list where I'm just going to have destin and weight, like so. The other one is going to take in the destination and the weight. And we have this designed this way because when I create a new edge, I'm going to be at a specific origin. And then I'm just going to say, put it with this adjacency list and just give me the destination. So saving that integer to represent the origin when I already know it, that's where we're going to save a little bit of memory. So it's going to be edge, and we say unsigned int. In fact, we can make this do const unsigned int and dest, and then const int ampersand weight in. And then we can say destin is equal to dest, and then weight is equal to weight in. And we put the parentheses. Is that the weight of the destination? Is the weight of the edge along of the weight edge itself, not of the destination? The destination is where it's going. The weight is how much cost it takes to get there. The last thing I want to show you, and this is yet another algorithms preview, is we're going to create an operator. I'm going to say bool operator equals equals. So we're going to compare whether or not the edge exists. And we're going to do const edge with a call by reference. I'm going to call this right-hand side. And then all I'm going to do is change it. So do I want, all I'm going to do is compare. I'm not going to change it. So do I want this method to be const? Okay, a lot of nodding of yes, very good. Const. And then here's what I'm going to return. And I'm going to explain why I'm doing this in a moment. It seems intuitive that I'm going to say destin equals RHS.destin. But I'm also going to say weight equals right-hand side and weight. While you all are typing this up, does anybody have any theories on why it is that I want to do that? Yes. Very good. That's exactly right. We might have a situation. It is entirely possible to have two edges that are outgoing from one vertex to another one. And that's another thing you'll learn about in a lot more detail in the algorithms course. An graph that has that property is known as a multigraph. And so while the rest of you are typing, what I'm going to do is I'm going to go over to the left board, your left, my right. And for those of you on Zoom, you'll be able to see it in the top right corner of the screen. If I have this kind of graph, and I can say A, B, C, D, E, and F. And they are at locations 0, 1, 2, 3, 4, and 5. Sometimes you can use an input to determine which way you want to go next. So sometimes I might say, if it's true, go back. Otherwise, so this can be a cost of 1, cost of 2, cost of 1. Let's say 3, 2, 4, and 6, right? But I can also say there might be another situation where I can take a different path to C and I can say 5. So just saying that I can get to C with that operator is not sufficient enough to solve that problem. I need to also be able to say that I can compare the two weights. And for right now, this is the common follow-up. For this specific graph at this level, we're just going to assume that you can't have two edges with the same weight. There's a lot of algorithms you'll learn about cleaning up graphs that find that and get rid of those edges. But for now, we're just going to say that this specific equation that I have at line 18 is sufficient to represent the graph in this course. Does anybody have any questions? All right, so let me go back up here. And what we're going to do next is we're going to start doing the foundations of designing our vertex. So the definition of weight is the cost it takes to get from one location, from one vertex to another. So an analogy would be if I wanted to drive to visit my wife's family in Indianapolis, it takes about 3 hours to get there. So the cost would be 3 hours. Hey, did that address your question? Thanks. So usually Sebastian sits over there. So please let me know if I've addressed the questions in the Slack. All right, so what I'm going to do next is I would like you, once you have this, and you can save it and update it. And I have the same thing in the slides where I describe, here's the edge code. There's the stuff with multigraph. Now we're going to write a vertex class together. So here, I want you to go into the file vertex1.h. So let me go back up here. Go into include vertex1. You're going to see that there's several different vertex files. And in this one, it's going to be mostly empty, but I have get and set methods that I've provided for you because we've already done get and set methods in a lot of detail. For a vertex, we can have several edges. You see here that I have dynamic array.h. We're going to use the vector that we designed. So everything in this graph is going to be based on code that we have previously written. So that means we are going to do a dynamic array, and we're going to template it. So the template is the data. I'm sorry, we have the edge, and that is the dynamic array of edges, and T data. So it contains the outgoing edges, but bear in mind we have this data versus structure, and we want to make absolutely sure that we can use this graph for any kind of purpose we want. So then the next thing I would like to do is we're going to go through and we're going to create a vertex. We're going to create two constructors. So let me leave that there. I apologize. Okay, there we go. So next I want to say vertex. And this is the default constructor. And we're going to use the default constructor that we created all the way back when we started working with dynamic arrays. And I said it was important to be able to have these default constructors. So now what we can see is we can abstract the complexity because we've already done that work. We don't need to do it again. And then the next thing we can do is we can have the default constructor of the data there as well. So that's going to be data, and that's going to be like that. The next thing we're going to do is we're going to have a vertex, and we're going to say const t data in, and it's going to be the same thing. Edges is going to use the default constructor that we wrote, and then data is going to be set equal to data in. So while you're finishing typing up that code, I will briefly describe the other two methods. The first method is get vertex value, and that allows us to be able to be able to obtain the data within the graph. Specifically within the vertex, and that method is labeled as const. And the other method is set vertex value, where we are updating the value. So we might be able to want to do that. We make some changes based on some training of an algorithm for machine learning. Being able to do get and set methods on that vertex is really important. Okay, does anybody have any questions? I see there's a comment in the type. You put vertex on line 21. That's probably what everybody else who's typing is telling me the same thing. So thank you for catching that, Matilda. And I saw all the other typing stopped, so that was likely what everybody was telling me. Thank you for catching that. Does anybody have any other questions or comments, or caught any other typos that Dr. Morrison put up? All right, so let me save that and update that onto the server. And so now what's going to happen is, and so that's just what we typed up here. These are the two methods that I've provided for you already. And then what I would like you to do is first I want you to run the command make test vert1. And what's going on in there is this a very simple vertex test driver. I create two vertices, and in fact, I can actually just vim it, so that way it's easier for you all to see. I can do vim src test vert1.cpp, and we see that what I've done here is I've created a vertex called hello vertex. I get the vertex value, so it should print out hello vertex. I then test using set vertex value, and then I print my result using get vertex value again. So when I run make test vert1, if we did everything correctly, it'll run, and you'll see that it prints out hello vertex and then updated vertex. So basically, what I design data structures or write code, this is kind of how I build it. I'll build it piece by piece and then test, so that way that allows me to easily narrow down where any errors that I've made are. So the next thing we're going to do is we're going to discuss adding and removing edges from the vertex. So what I'm going to do is I'm going to show you vertex2.h. And in vertex2.h, what I have here is I have the first method is add edge. So this edge, I take in a destination, and a weight. So just to reiterate, in this case, at a specific vertex, I already know the origin because that's where I am. The destination and the weight. And what I do is we use the pushback method that we wrote, and I create a new edge, and I push it back. Does anybody have any questions on that? The next thing I want to show you is remove edge. So one thing, and I'm going to go back over your right, my left. So let me go over here. And if I wanted to delete an edge from the graph, so let's say I wanted to delete D, and then later say, okay, I'm going to update this so that way B, it goes to E, like so. But I had this adjacency list, and it uses vectors to indicate where everything was. So before I had 0 was A. Let me make sure I can write. That's better. Okay, that might be good enough. 1 is B, 2 is C, 3 is D, 4 is E, and 5 is F. We learned when we were designing our own dynamic array that when we deleted everything, that it brought everything closer together so there are no empty spots, right? So what ends up happening if I delete D out of the graph, it will also impact these. So this will be now 3 and 4 in a dynamic array. The issue with that is all of the edges we put in had that destination. Remember that .destin that we just wrote? They're all set to the old edges, which means if we wanted to actually go through this whole process of deleting everything, we'd have to check every single edge every single time. And we'd have to update it, so we'd have to know how to do that. So that can take a potential significant amount of time. We're going to reduce that by using the same concept that we did in hash tables. We're going to do some lazy deletion. So what we have, I have a deleted, bool deleted is false. And I'm going to iterate through the edges. And if that edge exists, so remember I still have that edge, that I can delete. So now I can still have as many outgoing edges and preserve the adjacency list representation. But then I'm going to mark that vertex as deleted. So that way it doesn't harm the rest of our graph. Does that make sense? So one thing you'll see with graphs is we're actually going to revisit literally every other data structure that we've designed up to this point. And so I have a friend operator that iterates through each specific edge. So let me go down here and tell you what it does. So it prints out a vertex. If the vert.valid, so what I want to show you in vertex 2 is I added a private member bool valid. Uh-oh, that's not good. All right, make it 22 more minutes. So then I had to modify the constructors to be able to say that initially it's true. And then if I delete it, it's marked as false. So then if it's true, I just print out all the outgoing destinations. So now what we're going to do is we're going to run test vert2. And in test vert2, I have the representation of all the bridges of Königsberg. So I have top river bank, left island, bottom river bank, and right island. And from there, I've created a dynamic array of vertices. And then I create that array and push it all back. And then I use the add edge method that I just showed you. I know where the source is because I'm adjacency list 0, and I add in the weight. So for now, they all have a weight of 1. And I add in all the edges, and I say that I can go both ways on the bridge. So I have edges going back and forth. And then I print the adjacency list. And then I remove the duplicate edges, and then we'll print it out again, just to demonstrate a unidirectional and multi-directional graph. So if I run make test vert2, and you should do this as well. So let me vim prob1.txt. So everything, that is what should show up and everything that you've coded contributed to this solution. So if you see that, you'll have prob 1 in your system. Does anybody have any questions? All right, why do we need the erase method? The erase method, so there's two different vertices. We have an array, a dynamic array of vertices, and in each one we have a list of edges. So when we're using erase, we are deleting the edge. So what I showed over there, I was able to delete the edge representation, but not lose track of the destinations. So I used erase to delete the edge, but I don't delete the vertex. So that's why we're able to keep track of that. So I hope that addressed that question. Please let me know if it did. So now for problem 2, what I'd like you to do is I'd like you to go to graph1.h. And in graph1.h, we're going to build the foundation of a graph. So in that file, so let me give you a moment. If you go to graph1.h, we're going to have the private members, and we're going to do the constructor. We're going to be able to show how we can do a vertex prior to any edge, and then we're going to show how to add an edge. But I'll give you a hint. It's the same thing that I just showed you in testvert2. So when I did vim testvert2, all of these add edges, these methods that I have up here for pushback, the vertex representation, I don't want to delete from this vertex, but I would want to be able to erase from the other ones. So that's where we're going to see the difference in how that will be able to be applied. So for a graph, we have to keep track of all of the edges. So we're going to do the same thing we did in testvert2. I'm going to use a dynamic array, and I'm going to do a dynamic array of vertices that's templated to class T. And I'm going to call it vertices. I'll spell vertices correctly. So that's the only private member. And we only need to do that. We're going to aggregate the classes to be able to say that I can represent all the vertices, and each vertex has its own edge. So therefore, constructing the graph becomes relatively simple. We can just do a graph and then have vertices as the only private member. All right, so does that make sense so far? So now we're really taking advantage of class aggregation. For adding the edges, we're just going to do the same thing that we presented in testvert2. I'm going to create a method add vertex. And that's going to do const t call by reference vertex data. And so what I will do is I'll create a vertex that's templated, and I'm going to call it the vertex. And I can call the constructor with vertex data. So now I've created a new vertex, and then I'm going to push it onto the back of vertices. Right, does anybody have any questions so far? The next method we're going to do is we're going to use both of the recordings and stitch them together. So it's going to be a little longer to get it up than normal, but we will do that. Okay, and this will stretch out, so it should be lectern PC, lectern. All right, so that is sharing everybody's face, which I don't want, but I'll bring this over here so everybody can see. So if I cd into lec15 and I vim vertex 1 dot include vertex 1.h, You can see that some of the stuff that I have here has been updated. And now what I want to do is I want to go into graph 1.h, which likely doesn't have any of my changes, but I'll just quickly go over them again. Private, we just create that vertex. And then constructor is graph. And then with, I see all the comments. I promise you, I'm trying to get to, I know they're, like, okay, so you can't see on Zoom. It should be sharing the screen. So everybody, what do you see? Do you see the comments here? All right, this, okay, wonderful. So when I move it over here, now the students in the back can't see. All right, so let's see what I can, oh, I don't think I know how to do this. On this, I should be able to state which one I want here. I should be able to. I'm trying. I heard the whistle. It's okay. I'm working on it. Video filter, video settings. I want to share screen. I want to share second window. Nope, that's even worse. Aha. All right, so you all should be able to see it now. Please let me know that did that work. All right, good news. All right, so let's keep going. Let me minimize that so I can see the Slack. All right, so here we have graph vertices, and I'm going to add the vertex. Let me go over this really quickly again, so that way we can do void add vertex. So I'm retyping it also, not just because I don't have it, but because also it might have gone out during the broadcast. We call this vertex data. And then what we did is we created a vertex, and I called it the vertex, and put vertex data. And then I pushed it back onto the vertices dot pushback the vertex. All right, so we now have one more method that we need to write in this file, and it's going to be this adding the edge method. So the friend operator is already provided for you. And what we're going to do here is I'm going to say void add edge. And now here I need the origin and the destination and the weight. So the reason why we do this is because origin will be used to look up the location in that dynamic array, and then we put destination and edge into that specific one using the add edge method that we wrote previously for vertex. So now we're using class aggregation. So what we're going to say is if origin, and so we're going to do some protection here. We're going to say if origin, if I spell origin correctly, is less than vertices dot length. I think it's, yeah, length. And destin is less than vertices dot length. And please forgive the some of these issues here with the it's not as normal in terms of looking clean. But what's going on here is I'm making sure that we don't exceed the vertex length. So now we're going to say vertices at the origin. So now we're going to use vertices.origin, And then we're going to say add edge. And now we're going to pass destination and weight. All right, so I have it saved. So we have vertices here. And so a question here, should dynamic rate be dynamic vertices instead of dynamic? Okay, so this, I probably got it right the first time. This should be vertex T there. All right, so let me scroll down and show you what this should look like otherwise. All right, does anybody have any questions? Does it, I know it's the tabbing is a little off, but does it make sense what I'm trying to do here? So now we're adding the edges, and now I'm going to compile and run it and see if it worked. And the way we're going to do this with problem 2 is we're going to do test graph 1.cpp. And at line 48, I made a mistake. Vim graph 1.h at line 48. All right, so is this the comment that's going to be in the chat here? Missing closing statement, parentheses at line 30. Thank you, Marcelo. And also thank you, Kian. All right, so that should do it. And it compiles, and if you have this done correctly, you should be able to vim prob2.txt, and we will now see a full graph representation of the bridges of Königsberg. All right, does anybody have any questions about, let me put this back up here. Does anybody have any questions about the code for graph 1.h? All right, I'll do the same thing. I'll check the Slack just to be sure. Okay, I don't see anything in the Slack. So I'm now downloading the slides so that way we continue here. The slides at line 15, converted PDF. And so now what we're going to do is, now that we have a basic idea of how we're going to do a graph, the way we're going to do the last 6 minutes of lecture is we are going to, we're not going to tell Adobe anything. They can leave me alone. Is we're going to talk briefly about this idea of depth first search. So in depth first search, what we did was we're going to come full circle. We are going to use recursion, and we're going to write the code for depth first search on Thursday's lecture to start. But what we're going to do is we're going to say, all right, I'm going to have the specific call. And what I'm going to do is I'm going to go to that first edge, and then I'm going to make a recursive call and continue to go until I believe I have found the specific edge. And we're going to keep going. When we reach the edge, that will the end. We don't have any more edges, and we haven't found the destination. What we will be able to do is we will be able to claim that we can recurse back up. And what this will allow us to do is will allow us to be able to figure out the specific depth first search path. And so what I'm going to do is I want you to walk through with you the problem 3. And we keep track of visited nodes. So the simplest way to do that is to do a for loop through the specific dynamic array. And what I want you to do is I want you to go in to Buddy again. And I want you to run, let me run clear. I'm going to run make prob 3. And this is going to bring up an exam type problem. And we're going to work through this together. And what I'm going to do is I'm going to minimize this and bring this up on the whiteboard. I'm going to bring up here. I'm going to say, all right, lecture, board, your board left. And now I'm going to say to the video, Wolf Vision Cam, that should do it. Nope. Class cam. All right, so that's going to be the board. And I'm now going to pin this to the screen, pin the second screen. Come on. All right, so now you should all be able to see that. All right. And so what I'm going to do is I'm now going to go over here and I'm going to take this and, okay, thanks. You just made that change without my permission. Cool. There we go. And so what I'm going to do is I'm going to walk through this particular graph and we're going to show how it is that we're going to do this representation. So this will be the last thing we do in this particular lecture. And so I'm going to move this over. Okay, so we now can see the entire problem. And I'm going to draw out the graph representation, how we will work through this in depth first search. So the way this will work is that we initially have a vertex of 0. It contains the value 31. So that's what that notation means. So we have 7 vertices. So we've got location 0, data 31. Then we have an edge that goes to vertex 1, and that contains data 18. So we have an edge here. Then we have vertex 2, which contains the value 7. And now we have an edge going from here. So we're now going to create vertex 3. For clarity, I'll move 2 up here. And then 3 is down here. That contains the value -2. And the crucial thing is, from vertex 1, we have outgoing. 3 is the first value, and 2 is the second. Does everybody see that? That's a crucial detail in depth first search. From there, we have vertex 4, which contains the value 8. We have vertex 5, which contains the value 7. And we have vertex 6, which contains the value 88. And so now 2 goes to 5. 1 goes to 2, and it also goes to 5. 0 also goes to 6. 5 goes to 6. 3 goes to 2. 4 goes to 2. 2 goes to 3. And 4 also goes to 5. So this is a pretty complex graph. So here's the way depth first search works. And this will be a good way to finish lecture. I will tell you right now that the answer is D. So you can put that in there, get your prob 3, run your test, and it'll tell you the number of points that you will get, and that will be the conclusion, and you'll have that completed. So if you get that number of points, that's sufficient. The way depth first search works, let me change the color, is that I'm going to start at 0, and I'm going to go to the first location in the adjacency list, which is the value 1. So I go from 0, and now I have 1. From 1, I start out in the order of the adjacency list representation. So which one do I go to first? What's the value? Yes. 3, absolutely right. So now I go to 3. Right? So now 3 is where I'm starting. And now we're doing recursion every time. This is what we're going to code. So 3, where do I go to next? Why do I have 5 there? Okay, so 3 should be, 3 should go to 4. And then 4, where do I go to first? 2, right? And so where does 2 begin? 2, we've already visited 3. So now we go to 5, and then 5 goes to 6. So that's how we get that result. So that's how depth first search works. So we're going to finish coding that, and then on Thursday, we're also going to learn about another algorithm called breadth first search. So what I'm going to do is I'm going to make sure I get that video, send it to myself, stitch the 2 videos together, the one I have on my laptop and the one that's on here, and I'll get that uploaded for those who watch later. Does anybody have any questions? All right, in that case, it's 2 o'clock. You're all dismissed.